So we're going to start our unit on rotation by talking about centripetal acceleration. And we need to remember some stuff. Remember some stuff from geometry. So if I have a circle, and let's say that I draw a segment of that circle, and that segment, or sector, whatever it's called, I don't remember, and I have an angle theta. We're going to be doing radians now, by the way. I have an angle theta, and I have the radius of that circle, and then I have an arc length, which we usually call what letters? Anyone remember?
L.
Starts with an S.
L.
S. Okay. There's a relationship between S, R, and theta. Can anyone tell me? You learned this in geometry. I know it's years ago now. The arc length equals R times theta. If and only if theta is in radians. Okay. If theta is in radians, this is literally the definition of the radian. Well, based on the definition of the radian.
And then that makes it so that whenever you have the arc, because then whenever the angle is the full circle, it becomes.
Yeah. If theta is 2 pi, right, then that's where the pi comes in, right? If theta is 2 pi, the arc length is going to be the circumference of the circle, right? Yeah. Now, what if we have an object that goes from this location to that location in a certain amount of time? Or really, what if that object travels an infinitesimally small little arc length in an infinitesimally small amount of time? Then I can actually do the derivative of both sides with respect to time. And I do the derivative of this guy with respect to time. Well, the r is going to be a constant, right? So I'd say that ds dt is going to be r times d theta dt. This is something that we did learn in AP Physics 1. ds dt, if we're ignoring magnitude, if we're ignoring direction and only considering magnitude, ds dt is what? What? What?
Angular velocity.
Well, this is an angular velocity. This is linear speed. I'll say speed because the direction is constantly changing. This is distance over time, right? So that's literally velocity. Or speed. You should say speed. R is just the radius. D theta dt. What's d theta dt, Gianni?
That's angular velocity.
That's angular velocity. And angular velocity gets the round dw. It's the lowercase omega. Okay. So if I have an object traveling in a circle at some speed, I can define it in terms of its angular velocity. And d theta dt just means how much angle it's sweeping out per unit of time, right? So if I go around, if I do one full rotation in 1 second, well, my angular velocity would be 2 pi radians per second. Right? It's just another way of saying speed, but it's spinny speed and not straight lining speed. Okay, so you guys remember that? So very often, whenever we see omegas, very often we end up substituting V over R, especially when we get to rotational kinetic energy. Because an object that's spinning, that's not moving translationally, will have an amount of kinetic energy based on that rotation, right? As we'll talk about, not today, but in the next couple of days. So this is just some basics you need to know before we start talking about what we're really going to talk about today. And this was, without the derivative stuff and the velocity and angular velocity stuff, this is just basic geometry, right? Relating radius, angle, and the arc that is subtended by that angle. I think that's the right terminology there. Don't quote me on it.
So on the next FRQ, if I say it's curvy speed and not straight line speed, is that okay?
You're fine, yeah. That'll work on the AP exam as well, yes. So can I erase all this? No one said no. Too late. All right. So let's actually talk about an object that's traveling in a circle. And I like astronomy, so let's talk about, say, a planet that's orbiting a star. And let's pretend that this planet has perfectly circular orbit. How many perfectly circular orbits do you think are out there in the universe? Zero. Yeah. However, there are largely circular orbits. The Earth's orbit is largely circular. If it was a lot more elliptical, then life probably couldn't happen because it'd get too close and then too far away, right?
Well, what if it's equally sized planet on the exact opposite side of the star, the exact same distance away? Then would it be circular?
No, because the conditions required would have to be exactly perfect.
Yeah,
And,
if they were exactly perfect.
then it would be in a perfect. We're going to assume circular orbits right now, so. Yeah.
I'm gonna say there's at least 30.
What?
Say there's at least 30 somewhere out in the universe.
Well, you'd have to have a perfectly spherical planet, and then you'd have to have an exact, and there is no such thing as exact, because when you get down to the quantum level, everything's uncertain, and so literally, let's assume a circular orbit here. Okay. So this planet is orbiting this star in a circle.
You have a perfect system.
Pretend that I've drawn a perfect circle.
That's pretty good.
And what I can do, I'm going to call the star the origin of a coordinate system in which I'm going to be making my measurements. So I'll have the x direction and the y direction. And so this planet has a position in that coordinate system. And the general position vector is r. Right? That's the general position vector. And that general position vector has components, an x component and a y component. There's my x component, there's my y component. If we have an angle theta here, my x component is going to be r times the cosine of theta. Y component will be r times the sine of theta. Right? Now this planet, if it wasn't moving, it would just fall into the star, and that would be unfortunate. And that's actually a very difficult problem. How long would it take a planet if it didn't move to fall into the star? That's a hard problem. That involves a nasty integral that I probably wouldn't be able to do now because it's been so long. But anyway. So we got this planet that's moving. Let's assume it's moving because it has to be moving to avoid falling in to the star. And so its velocity vector would be exactly tangent to the radius. Or it'd be tangent to the circular path, and it would be at a right angle to the position vector. Right? Y'all with me? So let's write this position vector as an equation using unit vectors, and then we will relate that to the velocity vector. So I'm going to write, and because the planet is moving, I can think of this position vector as being a position as a function of time, because it's constantly going to be changing, right, as the planet moves in the circle. So I can say the position of the planet, or any object moving in a circle, this applies to any object in uniform circular motion, which means that r doesn't change, right? If you're in uniform circular motion, it just means that the radius is constant and the speed is constant. Now, if I wanted to express this in unit vector notation, I would write the x component, which is r cosine theta, times the unit vector in the x direction, I hat, plus, now we're doing vector addition, right? I want to express this vector as the sum of the two component vectors. The x component is r cosine theta times I hat, telling me that it's in the x direction, plus r sine theta times j hat. Cool, cool? All right. So if I want to relate the position vector to the velocity vector, or the position function to the velocity function, what do I need to do to the position function? Do the derivative. And so I'm going to derivatize both sides here. So when I do the derivative, dr dt, that's going to be the velocity. That is a velocity that's going to be as a function of time, right? Remember, the speed's going to be constant, but these components are constantly going to be changing. So these components are constantly going to be changing. Now, what's the derivative of r cosine theta I hat? If I want to find, let's say what's the derivative of r cosine theta times I hat?
Wouldn't it be?
Only r the derivative is a constant, right?
What's that?
It's a constant, so you just pull it out of the
The
derivative.
theta is not constant.
R's constant, theta is not constant.
It would-
With time, we're doing the derivative with respect to time. As time goes, theta is constantly changing.
Be
Oh, right.
Negative R sine theta I hat times d theta over d.
I wasn't expecting that. Negative R, so good job. Negative R sine theta
I hat.
times
Okay.
d theta over dt times I hat. Why do you say d theta over dt? That's the chain rule, right? Theta, I could, and maybe I should have. Theta itself is a function of time, right? So if I do the derivative of cosine theta, theta itself is a function of time, so I have to do the derivative of cosine, which is negative sine, times the derivative of theta as a function of time, which is just d theta dt, right? Does that make sense? Just applying the chain rule. So I end up, the derivative of this is going to be negative r sine theta d theta dt times I hat. And you can put the d theta dt out on the outside. That's fine too. And then what happens when I do the derivative of the right side? What do I get? Plus r cosine theta d theta dt times j hat. And I can rewrite this, if I remember what we talked about in the beginning of class. D theta dt is literally the definition of what angular quantity? Angular velocity, omega. Roundy w, curly w. Yeah.
And you can also pull stuff out and make it simple.
Yeah, so let's rewrite this. Let's rewrite our velocity function. I can pull out, I can have negative r and then omega times the sine of theta times I hat, right? Because d theta dt again is omega. And then plus r omega times the cosine of theta times j hat. You with me? All right. Now let's, just for the fun of it, let's determine the acceleration function. Let's talk about the acceleration function here. How do I get the acceleration? The derivative of the derivative. You could say the derivative of the velocity function or the second derivative of the position function. So it's going to be the negative derivative with respect to time of our velocity function, which is going to be, what's this? Negative r omega. Actually, yeah, negative r and omega, those are constants. And then times the derivative of sine, which is cosine. Theta times omega again. I'm going to go ahead and write d theta dt.
Just put omega squared.
Yes, I'm going to do that whenever I rewrite this. Yes, times I hat. And what do I get when I derivatize this side?
Minus r omega
Minus r omega
squared
sine theta d theta dt, which is going to be omega squared, times j hat. Right. All right, so let's rewrite that. My acceleration function is going to be negative d theta dt is omega times omega, so I get negative r omega squared times the cosine of theta times I hat minus r omega squared times the sine of theta times j hat. Now watch this. I'm going to factor out an omega squared. I'm going to factor out a negative omega squared.
negative r omega squared.
I'm going to leave the r in there. But you could. So I factor out a negative omega squared, and then on the inside I get r cosine theta times I hat minus plus, and I factored out a negative, plus r sine theta j hat. Does this seem familiar?
Oh, it's that one up there.
It's the position function. Right? So I can actually simplify this a lot more and say that the acceleration as a function of time is simply negative omega squared times the position function as a function of time.
You had different signs, right? So you
Wait, what?
So like if you tried to do,
Or would it?
if you tried to substitute that for the velocity function, you couldn't because you would have different signs, right?
Yeah.
Yeah.
But check out what I can do here.
And that,
What I can do, and let's just talk about the magnitudes of these now. At an instant in time, let's talk about the magnitude of the acceleration and the magnitude of the acceleration and the magnitude of omega squared times the position. It's just omega times r. Right, if I'm just talking about the magnitudes here. Well, I also know omega squared.
yeah.
Well, don't I know that omega, as we talked about a second ago, omega is v over r? Right, that's what we talked about at the beginning. V is omega times r when we were just doing basic geometry. So if that's true, then the acceleration is omega squared. So it's v squared over r squared times r, or the acceleration is v squared over r. And if we wanted to be a little more rigorous with it, which we're not going to be, it points towards the center of the circle for reasons that maybe we'll talk about later. And there's our centripetal acceleration formula equation that we've used this year. Even the new students, I had to tell you, this is a centripetal acceleration, and that we'd learn where it comes from later.
That's really fun. With the way the numbers are, the fact that it's just negative something times the position's function makes sense since it should be the opposite of the position.
Yeah, and you can actually if I take this velocity vector and then wait till the planet's here and draw that velocity vector, and then just find the acceleration by delta v over time, then that vector, the difference between those two velocities, points directly towards the center of the circle. Yeah. So maybe we'll talk about that in a little bit if we have time. So does that make sense? Good times, right?
Very good.
Cool. So are you going to have to do this on the exam? No. But this is kind of like how a lot of college lectures will go, where your professor will be like, this is how we get this. Now do a homework problem that involves a bunch of applications of that, right? So yeah, this is a proof, right, of an equation that we used last year that we're going to be using this year, that we've already used this year. And it's fun. This is fun physics, in my opinion. All right, can I erase all this? May I erase this? You guys talking crap? No sarcasm is allowed in this classroom. We are all above sarcasm. Okay. All of us are above any form of sarcasm. Okay.
For sure.
We talked about theta can be a function of time. It could be delta theta, which just means overall angular displacement, right? Which is like theta minus theta naught. So if I have, say, an object that's going to be traveling in a circle, I'm just going to be defining some angular variables now, and then we'll do some angular kinematics. So if I have an object that starts, let's say, at this position and ends at this position as it's moving in a circle, well, theta naught, if this is my position r naught, theta naught would be this angle. If this is my final position r, then this would be final theta. And then delta theta would just be the angle through which it actually moved, right, between those two positions. So that's what I mean by delta theta here, theta and theta naught. We already talked about on the macro scale, d theta dt is omega. But on the micro scale, that's the micro scale. On the macro scale, delta theta over some time interval delta t, but usually we just write t because we assume t starts at 0. That's also omega. Right? And as we talked about, d omega dt or delta omega over delta t or just time interval, that's angular acceleration. This is angular velocity. This is essentially, theta is essentially angular position, right?
And that's alpha?
And this is angular acceleration, which is lowercase alpha, which is like the fishy. Many people call it fishy. So when we're talking about translational motion versus angular motion, or more rigorously, spinny motion, translational position, or sorry, I should say, what actual quantity we're talking about. If I want to talk position, the translational variables are x, y, z sometimes. The corresponding angular, why am I doing that? The corresponding angular would be theta. We'd specify angular positions with theta. Do you guys do spherical coordinates in calculus?
I think we would have, but I think
Okay.
I'm.
Because if you ever have to like calculate an orbital for like the electron cloud for an atom, like you usually don't specify it with x, y, and z coordinates. You specify it with a position vector length, and then the angle that it makes with the one with two of the axes, right? And those spherical coordinates. So theta is what usually one of those variables, and then phi or phi, however you want to say it. So that's positions. If we're talking displacements, that's just our delta x or delta y. For angulars, delta theta. If we're talking velocity, translational velocity is v in the x direction, v in the y direction. Angular velocity is omega. It is a vector, and we'll talk about that in a minute. Angular velocity is a vector. We didn't talk about that last year. And then we have acceleration. Acceleration is acceleration in the x direction or acceleration in the y direction. For angular acceleration, it's fishy.
What about centripetal acceleration?
Centripetal acceleration is a translational acceleration.
Okay.
It just so happens to be pointing in the perpendicular to the direction of motion. So I know I talked about that at the beginning of the period, and then I'm kind of leaving that beside for a few minutes, and then we'll get some practice with that when we do our next assignment. And then, so yes, centripetal acceleration actually would go here because it is technically, it causes angular motion. It can cause angular motion, but it does point in the plane of motion. And we'll see that fishy does not point anywhere in the plane of motion, strangely. And then we got, I'm missing one other variable here. What other kinematic variable is there? Time. And so translational time is t. What do you think angular time is?
T.
It's also t.
What?
Why? Because it's a scalar. It's the only scalar here, right?
I like angular time better.
Because it's a scalar, its direction, it doesn't have a direction, and so it applies whether we're dealing with rotating motion or translational.
I don't know, I kind of like.
Well, I mean, if we start talking about the fourth dimension, your translational time.
Do you really want to start talking about the fourth dimension?
Was it time a function of velocity?
What's that?
Couldn't you say time is a function of velocity because of like quantum mechanics?
I don't.
Like, isn't it like if you get like closer to speed of light, like we're talking about like time?
Yeah, that's yeah.
But I guess that's more like.
And then once you pass the event horizon in a black hole, once you're close enough to the singularity, time and space actually reverse and become each other mathematically. What that looks like in the real world, who knows?
Is that like a frame of reference thing, or is it like a actual?
That's like in the actual mathematical terms. The one that represents space ends up becoming time. The one that represents time becomes in units of space. Yeah, it's yeah, stuff like that that led me to decide that, you know, maybe a physics degree is not for me. Which is funny because now I'm teaching physics.
So you're telling me a bachelor's of arts in physics is useless?
Difficult? No, it's very useful.
Oh.
I don't have one. I know people who got physics degrees that then go into investment banking and other things where they're not hiring them for their business knowledge, they're hiring them for their problem solving knowledge. Because if you can get through a physics degree, you know how to solve problems.
Let me find the rate at which this $100 bill enters the cash register and find the angular velocity.
No, it's more like what the problem is, how to maximize the investments of our clients. And then, yeah.
Let's find the length of the spine.
You guys are silly. Okay, so notice here, let me write a couple more things. Because this is what your next quest assignment. It's not going to be that long, but it is going to involve some of this. Translational, I got something like final velocity equals initial velocity plus acceleration times time. This is why we're not going to spend too much time on it, because kinematics for us is pretty basic, pretty easy. But angular kinematics is also a thing. And so I can say final angular velocity equals initial angular velocity plus acceleration times time. Fishy time. And then I have final position equals initial position plus initial velocity times time plus 1/2 the acceleration times the time squared. Final position equals initial position plus initial velocity times time plus 1/2 the acceleration times the time squared. And finally, final velocity squared equals initial velocity squared plus 2 times the acceleration times final minus initial position. Final velocity squared equals initial velocity squared plus 2 times the acceleration times final minus initial position. Works exactly the same way, the kinematics. You can prove that to yourself. I'm not going to do any more proofs today, though. So your next quest assignment is going to deal with some angular kinematics, some centripetal force, centripetal acceleration stuff. I'm going to save centripetal force to the next one, next quest assignment.
Centripetal force is not a force.
No.
Yes, it is.
Centrifugal force.
Centrifugal force is not a force. You got it mixed up. You failed for today.
It says gravity is not a force. How is centripetal force a force?
We consider in this class gravity to be a force.
But it's not.
But it's not. But it can be approximated as a force using Newtonian mechanics, which is what this class is all about.
Basically,
You never learn the non-force part of the gravitational force unless you're majoring in physics and you actually take relativistic physics.
Oh god.
Okay.
we can just joke about it.
How many people in here are actually doing physics?
One.
Oh god.
Okay. Yeah, so you'll be doing relativity. You'll have to learn relativity. Okay. So, one thing I want to point out, I said that obviously these guys are all vectors except for time. Let me put time in its own little category. These guys are all vectors. These guys are all vectors. Okay, last year, when we were talking about, say, a rotating disk, if you actually did stuff after COVID hit and I was asking you to do stuff.
We have like problems with our balls.
So, if I have this rotating disk, last year, we would say that, let's say its motion is like this, and we call that omega, okay? Or if we're looking at it from the top down, and it's spinning counterclockwise, we would say that's omega, the direction of omega. Omega is a vector. This arrow is not a vector, because it's not a straight line. This arrow is not a vector because it's not a straight line. It wasn't a huge deal to talk about vectors last year, unless I did. Did I talk? Or you? Okay, maybe I did. All right. Yeah, you got to use the right-hand rule. So it is a vector. It is a vector. And if I want to talk about omega, and let me actually use a better, before we go to it, and before I talk about the right-hand rule, let's talk about let's go back to circular motion. Let's say I have an object that's traveling in a circle.
What we had whenever we went to COVID was simple harmonic motion, and that was what was.
Oh, so we did get through rotation.
We were at like the end of rotation whenever.
Okay, okay.
Yeah, simple harmonic motion is difficult.
That was, yeah, rough.
Yeah, it's even more fun in this class.
Well, it was difficult because we were on.
Yeah.
Oh, it's awesome in this class. It's one of my favorite units because that's when we get to our first real differential equation. Our first actual fun differential equation. You can talk about any simple harmonic oscillator,
Like,
You can take a ruler and do this. That motion, an object moving in a circle, any repeating motion over and over will obey the same equation. The same equation.
because I remember spending like.
You can dig a tunnel all the way through the earth and jump in. And then the motion that you would experience going in and out of the earth, back and forth from here to whatever's on the other side and then back, that motion will obey the same equation.
Well,
I
if
just-
you did that.
It's good stuff.
Remembering-
Let's talk about today. Okay, so I want to define the angular velocity vector. There's a vector in terms of r and v. And to do so properly, we need a new vector product, or a new operator involving vectors. We had one new operator already, the dot product.
Cross product.
This is going to be the cross product. So omega is defined as, so I'll do the 3 lines, means defined as. It's also defined as d theta dt, but it's also defined as the cross product of r and v. Now, just to remind you guys of something, work, say we got a constant force over a distance, work is F dot delta x. Right. F dot delta x is the same as delta x dot F. You get the same result. Same result. That does not apply to the cross product. Okay. R cross V is not the same as V cross R. They're related, but they're not the same. Okay.
But it's two vectors.
What's that?
We're doing different things from the different vectors. Or different parts of it.
I don't know what you mean.
Never mind. I'm just letting you do it.
So the angular velocity is the cross product of r and v. Now, the magnitude of omega will be r times v times the sine of the angle between them. So just like the dot product of a and b is ab cosine theta, the cross product is the first vector times the second vector times the sine of the angle. That's the magnitude, but the direction we find using the right-hand rule. So the first step in using, and we're going to be using the right-hand rule a lot when we do E and N, because magnetic forces, if you have a charge moving in a magnetic field, if the magnetic field points towards you, it'll move in this plane. There's a lot of perpendicular stuff going on. Okay.
The resting heart rate.
Yes, the direction of the resting heart rate. The direction of the right-hand rule. Your first step, there's a couple ways of doing this. This is the way that I do it. Point your fingers. And I like watching you guys when you take the test over this unit, because I'll watch you guys be doing stuff with your hands. It's kind of funny. Point your fingers in direction of first vector. So in this case, I point my fingers in the direction of r. Your second, you curl your fingers. By the way, curl is going to be another operator that we'll talk about in this class, but you'll really delve into when you get to college. You curl your fingers in the direction of the second vector. And you maintain the same direction. So you put your fingers in the direction of R, curl them in the direction of V, so they point in the direction of V. Your thumb points in the direction of omega. Or your thumb points in the direction of the vector that is formed by doing the cross product. So in this specific diagram, if I wanted to draw the vector omega, it would be a vector that literally comes out of the board, right? You guys see that? Fingers in the direction of R, point your fingers in the direction of V or curl them towards that direction. My thumb points in the direction of the vector. Notice if I did it the other way, fingers in the direction of V, and then I took R and I put it over here because you can do that with vectors. You move them around when you analyze them. I move R over to here, fingers in the direction of V, curl them in the direction of R, my thumb points into the board. So V cross R is actually negative omega. It just points in the opposite direction. Now, why does this stuff work? We probably shouldn't get into it, but we can. Maybe there'll be a little bit of time left. What's that?
Because right-handed people are superior.
Yes, yes. Are there any left-handed people in here?
Inferior.
So you can use the left-hand rule. Just know that it's exact opposite. Everything's opposite if you use the left-hand rule. Okay. So here's some things though. The cross product. Remember the dot product. The result is a scalar, right? They call it the scalar product. The dot product, the vector. The cross product is also called the vector product because its result is a vector, right? And let me just talk about some geometric interpretations of it. Let's say I have a vector, let's just call it vector A, and then I cross it with vector B. I cross it with vector B. So I would point it in the direction of A, curl it into the direction of B, my thumb points out of the board. If I wanted to indicate that direction, I would put a dot and put a circle around it. That would be the direction of A cross B. And it is a vector. Why is it like that? Well, because think of it like an arrow. If it's coming out of the board or out of the page, we got to do 3 dimensions now. We're in the realm of 3 dimensions. It's unavoidable. If you have an arrow coming out of the page, then you see its point, right? If it was B cross A, well, let me draw another one. If I instead had B and then A, no. I have B, let's just say, let's call it C. C and then D. Point fingers in the direction of C, curl them in the direction of D, into the board. The resultant vector would be into the board, so you draw an X with a circle around it. That would be C cross D. Why into the board? Well, if an arrow is pointing away from you, you see the fletching, or the arrows, right? So this is just the general rule. This is the convention. Vectors that point into the board, into the page, into the computer screen. They're symbolized, this is a vector, but it's 3-dimensional, and the only way to draw it is as moving away from you is a circle with an X in it. That just means the arrow is pointing away from you. If it's the dot, that means it's pointing towards you. Okay. Geometrically, the magnitude of A cross B, which is RV sine theta, would be equal to the area formed by the parallelogram. This area here is the magnitude of A cross B. You don't use this that much, but that's a geometrical interpretation of it. And that area will, in fact, be equal to the magnitude of R times the magnitude of B times the sine of the whatever angle is between them.
I feel bad for whoever had to figure that out.
Oh yeah, it's tough. It's tough. I knew it at some point, kind of well, but I've forgotten it.
I think it's pretty funny.
Have you guys done matrices?
Yeah.
You deal with matrices?
In algebra 2, I think.
So you probably didn't deal with determinants at all? The determinant of a matrix? Because to truly get the magnitude of a cross product, it involves determinants of a 3x3 matrix. Actually, it involves determinants of 2x2 matrices, which are part of an overall 3x3 matrix. So it's much more complicated than what we need to do in this class. What you need to know is the direction. You need to know how to get the direction using the right-hand rule. And you just need to know that the magnitude is not AB cosine theta, but AB sine theta.
So is that linear algebra?
Matrices, that's linear algebra. And I'm telling you, 3 blue, 1 brown. His playlist on linear algebra will make some of that stuff much less mystifying. And don't be thinking, oh, linear, that's easy. Algebra, that's easy. Linear algebra must be easy. Oh, no. Unless you're way smarter than I am. Yeah.
So confused about the right-hand rule. I don't.
Okay, so
What was it?
you say you weren't here?
What was your last one?
Okay. So let's just talk about vectors in general. Doesn't need to be no, let's actually use actual. Let's say, again, we have an object that's moving in a circle. Sorry. Time this class, I only got like 5 minutes, right? Let's say we have an object at the end of a string that's just moving in a circle, or it could be a planet moving in a circular orbit. Any object moving in a circle, where the center of the circle is the origin in our coordinate system. Okay. So we can specify the position of that object with a position vector r. Now, if this object is moving in uniform circular motion, its velocity will be exactly perpendicular to that. But the cross product, you don't need it to be that case, but we see that for this unit, this is the case that we see most often. So if I want to find the direction of omega as a vector, it is the cross product of r. It's r crossed with v. This is how they say it. Okay. So to specify, and for our purposes, all we need to do, the reason that we do the direction of the cross product is so that we can specify an angular velocity with a single straight line vector. Okay. And that straight line vector will tell us whether the object is moving this way or that way. Okay. It could be a rigid object that's actually rotating, which we'll get to. So if I have a disk that's rotating this way, I need to be able to specify that rotation with a single vector. And eventually we get to angular momentum, right? You can have the angular momentum of an object that's spinning, but that angular momentum needs to be a single vector, and curvy vectors don't exist. Vectors must be straight lines. So I want to be able to talk about either the circular motion of an object or the rotation of an object in terms of positions, velocities, and accelerations with straight line vectors. The only way to do that is with a vector that is perpendicular to the plane of motion or plane of rotation. And to specify that direction, the cross product was invented. It's more complicated than this, but for our purposes, this is good enough. And to specify that direction here, I would say you point your fingers in the direction of the first vector, which is r, just by definition. You curl them so that they're pointing in the direction of the second vector. Notice if it was pointing out that way, it's fine. If it was pointing in this way, it's fine. The vector points in the same direction. Fingers in the direction of the first, curl them in to the direction of the second. Your thumb points in the direction of the angular velocity in this case. Okay. If I had another object that's, say, moving in the opposite direction, so that's that object's velocity at that time with this position vector at that time. Now this guy's moving the opposite direction as this guy, so the vector should be pointing in the opposite direction. Instead of into the board, like this guy's angular velocity vector would point, this guy's angular velocity vector should point out of the board. And no, this guy's points out of the board. This guy should point in the board because it's going in the opposite direction. It's rotating, or it's moving in a circle in the opposite direction. So fingers in the direction of R, curl in the direction of V. My thumb is now pointing into the board.
So your thumb has to be like straight out.
Yeah, yeah. Some say pointer finger first one, middle finger second one, thumb in the direction of the actual vector. Okay. And then you can extend this to angular acceleration. Is also the cross product of r, the radius, and the linear acceleration. Okay. If the angles, if we have perfectly circular motion, omega is simply r times v. Fishy is simply r times a. Right? But that's the important part for now. Okay, there is a quest assignment that's open. You can get started on it if you want. We're going to work on it in class tomorrow. That involves angular kinematics and centripetal accelerations. Just to get that. We're not going to spend much time on that, though, because we need to move on to our more robust parts of our rotation unit. Okay? That's my story. Have a good day.